Okay, so let me start by first thanking the organizers again and really thanking them because some of you may not know this. I spent a year here on sabbatical just a year ago, and so it's really nice to be back to this wonderful place. I think it's a fantastic spot, and I'm very happy to be back here again. Okay, so I'm going to talk about the dynamic color model, but I'm going to spend a fair bit of time emphasizing how, to some extent, this is the epitome of a multi-band superconductor, although you might not recognize it as such, so I'll explain as I go along what that means. The motivation really goes, I mean, there are many motivations, and I won't get into it in great detail, but I think more and more all of us are looking at this TC versus timeline, and you know, we're starting to insert our favorite superconductors, and we're realizing that this is becoming quite a zoo of different classes or different families of superconductivity, and we're coming up with various mechanisms specific to each class, and because of the peculiarities involved in each class, so the structure, the three-dimensionality versus two-dimensionality, and so on. And it's perhaps time to stand back and look for underlying more universal type themes. And so this delineation of high temperature and conventional or low temperature perhaps is not so well delineated as perhaps previously thought. So I didn't question how well we understand the theory of conventional superconductors. So what I will do here, I am going to skip this overview of Ellie-Ashburg theory and BCS. Most of you have some familiarity with this. One of the reasons why I like to give this overview is to convince you that I know about this theory, and so I know what I'm talking about. I'm not dismissing the conventional theory out of hand, because there's a lot of evidence that favors it, yet I still think something is missing. So I'll focus, I'll use cuprates as a case study example, and then go through some various more qualitative more than quantitative arguments. The only thing I want you to recall from the conventional theory, because this will come in to some, one of the experiments that I'll describe, which I think is a bit of a smoking gun still, even though it's more than a decade old, is this notion of conventional superconductivity sort of grounded in a sacrifice of kinetic energy so that we can gain the potential energy. And it's this smearing of the distribution function, which seems to be a bad thing to do if you were just focusing on kinetic energy, but is good overall because we gain in potential energy. That's the standard paradigm associated with BCS theory, and that's the one that maybe has come into question. Okay, so let's go right to the cuprates, and there's this important process that occurs often at the beginning of every new discovery when theorists start to look at things, of reducing something that's very, very complicated. This is the structure of one of the perovskites, down to something less complicated, and eventually to even less complicated. So what I've drawn here is a simple square lattice, which is supposed to represent the copper-oxygen planes. And now, because of work of Phil Anderson and Zhang Rice, the proposal is that we can understand what's going on here by focusing on a simple square lattice and focusing on something called the Hubbard model. So the Hubbard model, as most of you know, is again the paradigm for what I was describing in the case of superconductivity, which is this delineation between kinetic energy and potential energy. And most of quantum mechanics concerns this sort of fight between kinetic energy and potential energy. And what Hubbard said was, okay, let's just focus on the short range interactions. So when two electrons are on the same site, then they'll pay this price U. But underlying this philosophy is that we understand the single particle properties, and that's sort of solving this part of the problem, the kinetic energy. And now we look back and say, wait a minute, we want to include interactions, and so let's include interactions as best we can, and that's what we do through the Hubbard U. And this philosophy, as I'll come to in a few slides, may not quite be right. In the meantime, of course, people have questioned whether this Hubbard model has the right stuff, as Doug Scalapino once put it. And so people have looked at nearest neighbor interactions, looked at modulated hopping, various variants that actually Hubbard himself looked at in his 1963 and subsequent papers. He even gave estimates for these and therefore said that they were small compared to the main energy scale U in this problem. So these are ongoing, and what I'm going to suggest is maybe something has been missed all along, and this was first proposed by Jorge Hirsch back more than 10 years ago. So this is what he called the dynamic Hubbard model, and I'll come to why that's referred to by that name in a short while. To explain what this is, I'm going to continually refer back to the helium atom. So simple atomic physics to understand what this is about at the local level. In helium, there are two electrons, and we often, even in my favorite condensed matter textbook, there's a nice periodic table that shows all these valences, and I've always appreciated that. And so it tells you that these two electrons are in the 1s state, but of course that's not really right at all, right? It's actually in a linear combination of these states. And so how does that come into play? Well, this is, I should add that currently I'm also involved in a project, I guess, at our university to bring the teaching and research worlds together. Okay, so most of us think we lead double lives. We do what we like, which is research when we can, and then somebody drags us off and forces us to teach. And this project is an attempt to sort of bring the two worlds together, and this is one example of that. So this work originated with two undergraduate students, and it's just driving home the point that I just made about helium. This is a calculation, it's a spectral decomposition. So it was an attempt at first to calculate the ground state energy for the two electrons in helium, which is known to be at minus 79 electron volts, using ideas that undergraduates are familiar with, which are these product basis states. Actually, they're not that familiar with those, but once you tell them about it, they become familiar with the idea. So this is the almost first and only example, at least at our university. I've been teaching the 3rd and 4th year quantum classes. This is their only exposure almost to a mini body problem. Two body in this case, but really it's a three body because of the nucleus. So the point here is that's the exact energy, and if you simply do the perturbation calculation that we often do in these classes and include the repulsion between the two 1s electrons, you get the energy down to a reasonably good value, because this starts off at minus 109 electron volts, if you don't take this into account, and you bring it down to minus 75, and that looks pretty good compared to the exact energy of minus 79. But that's still way off, okay? And if you calculate the total probability of the exact wave function, so this is a spectral decomposition, this uses the Hillerist state for the helium atom, it's about 93% in the 1s state, but there's an entire almost 5% which is in the next one, which is a 1s, 2s. Okay, so why is this important? Because when you compare it to experimental values, that 4 electron volts, that discrepancy remains between the naive estimate, and 4 electron volts is 46,000 degrees Kelvin. And we're trying to understand a phenomenon at about 100 degree Kelvin or less. So there's no reason why you shouldn't worry about this. So this is sort of restating what I just said. But let me use this figure to emphasize again what I'm saying in terms of the lattice model that I was discussing back with Hubbard and the variables. That lattice model corresponds to these blue atomic sites, and I'm using one-dimensional for clarity. Thinking of them as helium atoms for the time being, we know there are these 2s states. If we were trying to describe a lattice with electrons occupying most of the, or half of the 1s sites, we would never dream of including 2 orbitals in this calculation. We wouldn't do a multi-band calculation. We would look at the single particle properties and we'd say, well, there's one band that crosses the Fermi energy, and that's the one corresponding to these blue orbitals. There's another band that's up about 10 electron volts higher. Why should we include that? Never included it in our minds. Then we stop and say, wait a minute, we want to do a better job, so we want to include Coulomb repulsion. So we do what Hubbard did, and we put in the U's. And that's what I'm claiming would be a little naive. Because based on the example of helium, when 2 electrons happen to be on one site, and even if this set of orbitals is not completely filled, when the electrons are moving around, there will be times when you face double occupancy. When that happens, we know what happens in the example of helium, of a single helium atom, that orbital expands. In other words, the 2 electrons here don't just stay put in the 1s electron states, they partially, 5% or so, occupy the 2s state. Okay, so that second band plays an important role. And it will play an important role in these lattice models as well, in analogy to a single helium atom. That's the premise of the dynamic covered model. Okay. So the way I'm just going to show you a few results, the way we've tackled this is both through exact diagonalization and dynamical mean field theory. I won't describe either of those 2 procedures, but this is an example with just simply taking 2 sites, and again, basically redrawing the picture on the previous slide. These are the sorts of things, the sorts of kinetic energy processes you have. We've included both T prime and T12. I don't know which one to include here to properly mimic this. Back in the case of the helium atom, if we stay on one site, we've presumably already solved that problem. We've already diagonalized it. So there's no T prime to speak of. But in any event, that's what we put in here. This was done by an undergraduate student shown on the right, Lindsay Forrest. So here are some just very preliminary results. You can calculate a U effective. I haven't written down the definition, but it involves the ground state energy for n and n plus and minus 1 electrons. And you can look at that as a function of the number of electrons. So there's 4 sites, so there could be a total of 16 electrons. And what you see is we did not achieve an attractive interaction where this would go negative for this particular sets of parameters, but what we can. All I want to show you is that we can calculate this, and it becomes more attractive the more electrons there are. Because the more electrons there are, the more you have to worry about double occupancy. So down here, where there's almost, with 2 electrons, if we start with 2 electrons with repulsive interactions, we get an effective repulsive interaction. But when you start crowding the lattice and forcing some electrons to make these transitions to the upper band, that's when you start getting more heading towards attractive interactions. Okay, so 4 sites, by the way, means you have to diagonalize a 4,900 by 4,900 matrix, so we're not going to get very far with this methodology, but it helps to understand what things are going on. This is work that's currently being done. You can also use dynamical mean field theory, and this is work by a graduate student, Chris Polachek. And again, here I just flash up the quasi-particle weight as a function of filling. So 2 is half filled because there are 2 orbitals. But I'm not interested in studying the properties of the second orbital, right? This is supposed to be all about the low energy orbital. So this is roughly full filling for that orbital. Of course it isn't. By the time you get here, there's mixing of, some of the electrons are partially filling the second set of orbitals, and most of them are filling the bottom one. Again, the point of this calculation is to show this strong asymmetry. Okay, we're all taught that electrons and holes are symmetric. You can just have a few holes and it's the same thing as having a few electrons. This model says no, that's not true. And you see this in the quasi-particle weight. Very few electrons have quasi-particle weight of 1. Very few holes, as you move over towards here and ignore this upturn for now, have a reduced quasi-particle weight. They're much tougher to move around. I didn't emphasize, and I should have perhaps back here, that you can't just model this effect with an effective U and leave it at that. Because in this process, for example, if this electron hops over to here, this remaining electron is now in an excited state. In this configuration, it isn't. But if this moves, that's in an excited state. And so there's a relaxation process, a polaronic process, if you like, that's involved in this as well. Okay, so that being said, most of the work we've done in this model has been in terms of an effective model, and that's what I've written here. So here now there's only 1 band of electrons, but there's this pseudo-spin degree of freedom at every site to mimic the second band. Okay, so what is this degree of freedom about? It says, well, obviously you'd like to be in the ground state for this degree of freedom. So you're just going to stay put down in this state, and that'll be that. Except when you have double occupancy, so Ni up, Ni down, then this term favors occupation of the upper state. Okay, so it's trying to model what I've been saying about the explicit 2-orbital model, that sometimes you want the electron to occupy the upper orbital, and this is now accomplishing that through a pseudo-spin degree of freedom, just something you're associating with each atomic site. And so this is really how you see this as being called a dynamic Hubbard model. The value of this Hubbard U is now variable depending on this pseudo-spin degree of freedom. Or in the older 2-orbital language, it's trying to incorporate that second set of orbitals. I like the other model better because it's explicit, and it's the microscopic model. On the other hand, this model is really centers attention on the lower orbital. That's the only set of electron orbitals involved at the expense of this pseudo-spin degree of freedom. So we've done a variety of calculations, mainly by my former graduate student, John Black. And so let me just put some of these down. So here I've actually included some straight Hubbard model calculations. So that's the light blue and the brown to emphasize these are particle hole symmetric. Same thing for a few holes as for a few electrons. But as soon as you start to add in this G is the coupling for the pseudo-spin degree of freedom. And notice it's a coupling to double occupancy. So it's entering, it's faithful to the original 2-orbital model in that it's involved in 2 particle properties. It's not involved in the single particle problem. Like I said earlier, if you focused on the single particle problem alone at the start and then decided to add interactions, you wouldn't be including this effect. And so this is really goes beyond that. So the emphasis here is electron-hole asymmetry. When you include more moderate values in this coupling, then I've redrawn it here. One of these is an analytical result, the others just depend on the parameters. But you see that that quasi-particle weight always decreases from near unity for a few electrons to some lower value, depending on the value of the parameters, for a few holes. Okay, so this is now a result which emphasizes single particle properties, and it shows up in the single particle quasi-particle weight. Okay, and coincident with that change here again is a function of filling. That pseudo-spin expectation value for sigma z goes way up. Instead of being down at in the ground state down here, there's partial occupancy up here, which again is something you wouldn't do unless you could gain energy in some way. Okay, so for the last part of the talk, let me just focus on one observable, which is the optical conductivity. And here are plotted some calculations from the DMFT. For very few electrons, density of 0.1, up to very many or very few holes, density of 1.9, you see there's a clear asymmetry. There's extra peaks out here, again due to this, in this calculation, due to this pseudo-spin degree of freedom. In the original model, this would have its origin in the fact that when that system absorbs light, there are various routes of absorption now, and some of those involve that second set of orbitals, and that's what this would correspond to. When there are very few electrons, no electrons are occupying that second set of orbitals, and so there's no secondary peak here that can be seen. This is a simple two-site calculation, a dimer calculation showing the same thing. Now you can have 1, 2, or 3 electrons. And with one electron, there is just this one peak. This is the Drude peak. It's displaced from 0 because of the finite size. When you have 3 electrons, you still get the Drude peak, but now you have these 2 extra peaks corresponding to those at the same excitations. How does this have anything to do with the experiment? Well, many years ago, there were these experiments done on the optical sum rule that's given by this formula, and for various conditions, this thing reduces basically to the expectation value of the kinetic energy. So this was a way of measuring the kinetic energy. And so, in particular, van der Mel's group undertook these measurements, and that's what's shown here as a function of temperature squared. And so these things are going up. This is just telling you that the Fermi distribution function is sharpening up as you lower the temperature. So that's why this is going up. So the kinetic energy is getting better. And then BCS theory at TC would have you go back. Remember that plot I showed you? I think I might show it again here. No, I don't have it. But the plot of the electron distribution function in the superconducting state was smeared out as opposed to the normal state, just like it's smeared out in the normal state because of temperature. So this goes back. When you look at experiments, these are original ones, and this is one from 2006, I think. Here's TC, and instead of coming down, like I just showed you, it goes up. Okay, and this was a sign that that paradigm I described from BCS theory seemed to have something wrong with it. So this experimental result is consistent with the ideas I just told you about coming from the dynamic covered model. I'm not going to show you that explicitly because I don't have time, but this here it is in a sketch done around that time, and it shows up as a violation of the optical sum rule. Okay, so this is for C-axis, but we focused on the in-plane. So it's as if there's extra spectral weight out here, and that extra spectral weight is coming from these, extra spectral weight loss is coming from the secondary orbital that I mentioned. And there's a phenomenology to go with this that corresponds to scattering rate clock. So a lot of this is consistent with the early experiments. And some of you may remember the microwave experiments that showed this big peak, and that was interpreted as a collapse in the quasi-particle scattering rate. this is all consistent, but at a phenomenological level with what I just described. Okay, so in summary, I tried to make the case that we need to understand the mechanism for superconductivity at a more basic level. An attempt to do that is with the dynamic Hubbard model. In the conventional theory, this would translate into a reinterpretation of what mu star is all about. Mu star in conventional theory is supposed to summarize all the direct Coulomb interactions between two electrons, and it's just some number. Okay, there is certainly more to it than that, but up till now, because we focused on the structure that comes in time from the electron-photon interaction, we've been happy with this approach because it seems to work. But I would claim there's a lot more to it than that. We find this fundamental electron-hole asymmetry and this paradigm of energy going through kinetic energy and not potential energy is, sorry, the paradigm is the opposite of that, but the suggestion is that there's some kind of lowering that's happening through the kinetic energy and not necessarily through the potential energy. And I'd like to thank the many collaborators, and here are the pictures. Some of them look happier than others, but they were all very happy when they did this work. Thank you.
Thanks for this nice talk. The paper is open for discussion.
Would you recover the particle hole symmetry if you introduce interactions between the upper and the lower?
If I introduce?
Interactions between the upper and the lower and the
No. No, the model we're using here does have interactions.
But it has hopping, but it have a...
Yes, I didn't take time to describe that in complete detail, but there's a U11, a U22, and also a U12. Yeah, no, it's because when you have very few electrons, you really don't have to consider this second band. But when you have very few holes, that is very many electrons, you have to consider the second band. And so processes that will come in that simply don't come in for a few electrons.
So to understand correctly, that essentially the main thing that happens is that the electrons are very unhappy to stay in the correlated orbital and they run away. But when there are many, many electrons, they run away in the high energy orbital, which would be otherwise free. So
yes.
You spill out charge from the correlated orbitals.
Yes.
So my question is it essentially everything? So is this the way, for example, we understand the energetic balance of the superconducting transition, or there is something more to it?
I'm not sure I understand what you're asking.
Yeah, let's say, so you have a simple curve, so you're telling us that you can understand the superconductivity, which is associated essentially to a lowering of potential energy rather than kinetic energy, or at least something which doesn't look like BCS at glance.
Yes.
So the question is, if the story is simply the charge goes away, do you have a simple cartoon for understanding this?
Well, the simplest cartoon is no, I've taken it out. I took a lot of this talk. I must have put it somewhere. So in this language, there is an energy scale omega naught corresponding to the pseudospin energy. And if you take that omega naught to be very large, an anti-adiabatic limit, then this entire model reduces down to the hole hopping model that Hirsch and I studied in the late 80s, early 90s. And that looks like BCS, except that it goes back to what was my comments earlier about Hubbard. Hubbard introduced in 1963 this term that was off diagonal. Okay, so it wasn't on site, it wasn't nearest neighbor, but it was a model that corresponded to an electron hopping, and the hopping rate depended dynamically on the presence of other electrons. Okay, and that shows up as an interaction which you can then treat via BCS theory, and that gave rise to superconductivity, and that's probably the easiest way to understand some of what's going on here, at least in that limit. It's an unphysical limit because this parameter is going to infinity, and we've done other calculations that I haven't shown here, bringing that model down from infinity from those ideas, and that's also consistent with pairing. And that's why I keep saying it may not be correct to keep separating out kinetic energy processes from potential energy processes, because that one has no mix. And it resulted in momentum dependence in the interaction, and it's a long story. But other than that, I can't give you a simpler picture than that. Yeah.
Is there another question? Another question? You have a question? I would like to thank you very much for this nice talk. It reminded me, I got a referee report once in a paper that I consider to be very important. And the referee said, this cannot be published because also a student of the third year's school in the graduate school can understand. So that is applied to your case. And then I would like to mention that we did in 92 with Akio Kotani, we applied the Anderson impurity model for a case where you have dx squared and dz squared. And dz squared is very far. But you apply configuration interaction, then you see you have quite an important occupation. And this was, I will mention perhaps in my talk. But it's very interesting. It reminds to me something that also Srinadi can remind, that Fano was always saying the important physics is in the basic physics. Thank you for your attention. So we are in time.
Yeah,
it's
very
about
well,
15. We have time for lunch now.